Hi everyone. Our project title is Robust Long-Term Learning via LLM-Guided Adversarial Augmentation. I am Aditya, Srijan, and Nikhilesh. Coming to the motivation, so in real-world data set, we often have a issue of some head classes having more number of data points compared to many tail classes. So model have achieved higher accuracies over the head classes, but perform poorly on the tail classes. If even if we try to solve the long tail issue, the adversarial vulnerability still be there. So robustness of these models are also very important. So we are going to present three papers: first on synthetic generation, second on robustness, and third on SynCLR. Starting with the first one, LTGC. So the basic idea is to use LMMs and LLMs to generate diverse content for the tail classes. Starting with the first module, which is the generation part. So in the first we use the tail images and feed it to the LMMs to extract the text, visual features and semantic details. We use this prompt and this template to so that we can get the structured output. Then we use these extracted feature and feed it to the LLM using this prompt to extend those textual features. Then there is a self-reflection part they have suggested, in which there is number checking module, in which the initial generated textual description was fed again with the updated list, so that we can get more number of description. Tail class, whichever has low number of data points. No, not text, images. Yeah. So images, so LLMs will give the textual description. So the number checking part, until we hit a particular number, this iteration process will go on. Then there is a repetition checking module, in which they use prompt 3 so that they can remove out those repetitive features. Then comes the generation part. So they used DALI text to image model to transform the descriptions into synthetic images. In this, they have used the iterative evaluation. So using this prompt 4, whatever the image they have generated and the features they had, they feed it to LLM and the generated image. Finally, they used clip image encoder for the images and text encoder for the textual features, and calculated the cosine similarity. If it's greater than a particular threshold, then it used in extended data set. Otherwise, they'll refine it using the prompt 5 and regenerate the image, and this process will go again.
When is prompt 5?
So if the similarity is below a particular threshold, they'll use they'll prompt for in the last part before the regeneration part. So they'll say the description is not.
Yeah, but my point is, who detects that the description doesn't see? How do they detect?
Cosine similarity.
Just by cosine similarity.
Yeah, between the
Okay.
Yeah. So they took the real image and the synthetic image of the same class and did the mix up augmentation, and finally they fine tuned the clip vision encoder with LoRa. In this, they have used these particular data.
Experiments are not too important. You go back.
Yeah, the baselines are important. So, in
But,
this
but before that, the balance mix
yeah,
part.
balance mix
Um,
is basically the to mitigate the domain gap between the real and the synthetic images.
yeah, so every new image or synthetically generated image is mixed up with an original image.
Yeah,
But in that process, how do they ensure that this is not countering the process of tail representation? Because original images may all be in favor of the head. So is this mixture component lambda? The lambda is sampled from beta of distribution, but is there some tuning of lambda such that it doesn't start favoring the head distribution again in mixing?
oh,
You
yeah,
don't want to undo all the work of, you have done so much for five level prompt based generation for the tail labels.
yeah,
Now after all that, if you do a mix up, which is, let's say, lambda isn't 0 1, but let's say it just turns out to be close enough to 1,
yeah,
right? So um, and they say it's beta, so beta can be 0 or 1, which is also dangerous. I mean, beta distribution. Um,
they
they
have
actually
kept open interval for some reason.
sorry,
They have kept open interval on the bit. I don't know for some reason.
that is okay, but it can favor 1 also, right, over 0.
Yeah,
So if it favors 1 over 0, then it becomes close enough to the original image.
yeah,
Again, we'll have a mount what? Yeah, I mean, you would like it to be a little close enough to 0, right? Closer to 0 than to 1. You want some asymmetry. This is just a symmetric distribution, right?
yeah.
Are you happy with the symmetric distribution? Is there a problem with this? Or is it okay to have a symmetric distribution? You understand beta is one is symmetric, right?
Yeah.
Is it a concern you see, or you're not understanding my question? So you have not critiqued from that perspective. That will still not make it biased towards the generative distribution. Okay. You need to think about it. Go ahead.
So they have compared these to just the clip-based methods, so that it remains uniform. The results remain uniform. Next, in this next step, in this they have shown the effectiveness of their iterative evaluation process. So these are quite important to this method.
Hello, my name is Nikhilesh. I'll be talking about this second paper, which is adversarial training under long tail distribution. So as we know that deep neural networks are vulnerable to adversarial attacks, and these attacks have some small perturbations in them which can fool the models, but which are essentially easily visible to us, but they don't work with the model itself. So adversarial training is one key defense mechanism for it, and it has worked well with balanced data sets like Cypher 10, Cypher 100, ImageNet, etc. And as he spoke, the real world images have long tail distributions. We'll see how this works well with it. So the naive adversarial training has min-max for formulation, where we have two loss function, uh, essentially the inner and the outer loss functions. So this could be the same loss functions, or this could be different as well. So like, for example, both could be binary cross entropy loss function, or one of them could be trades with KL divergence, etc. So the outer loss function is the one on which we try to minimize our loss function to get effective parameters for the classification. whereas the inner loss function will try to maximize it in order to obtain an adversarial x dash, or it's an adversarial example generated, which is a copy of x which has some sort of perturbation in it. We'll try to maximize this. Okay. So Robal is one of the method which was tailored for long-tailed adversarial training, but it is quite complex and it is not very efficient and takes a lot of time. So we'll analyze it. We'll do the ablation procedure on it to identify which are the best components of it. So what we found out is that the balance softmax loss is the most important part of it, which gives us the best results. Even if we take the adversarial training with this balance softmax loss, will certainly get a good performance, as well as will get efficiency, and it will be less time consumable as well. So the normal softmax is, we just have weightage on it. So from the paper, the authors, they formulated a loss function which combines the binary softmax loss along with data augmentation, and they got a very good accuracy and a proper robustness as compared to the original Robal, which is over here, and the one that they got is labeled in form of a star. So this was go back one. So this was formulated on a wide ResNet 3410, which increases the layers get multiplied by 10, which with each successive as we proceed forward in the neural network. So it was almost 6.6% uh, uh, better at robustness with auto attack adversary. So even though it's a good mechanism, it still suffers from robust overfitting. So what do? We do is we use data augmentation. So as we know that data augmentation has helped in balanced data sets, augmentations have worked very well on this long tail distribution as well. So we have augmentations like mix up, cut mix, cut out, random augment, trivial augment, and auto augment. So these all have worked very well with long tail distributions. So next. So we'll look at the key contributions and key components of our adversarial training of Robal, which was devised in 2021. So we the neural networks that we used earlier, it had logits which were used in the softmax loss, which were of the first form, which were just linear, standard linear classifier, which were used for the loss function. It had it wasn't balanced well for the balanced well for the higher distributed as well as the lower distributed uh, classes. So what we do is we normalize them and we formulate this cosine classifier, and which has these three components: this theta I, bi, and s. And s is just a learnable fixed scaling factor, which we could set to any number first, and as we go further, we can change it and rescale it to get a proper function. So balance of softmax loss, which is the most important term, which has given us this proper robustness fitting. So what we do is that in the bias term, which was in the earlier slide, we input this TB times log ni. Ni is the number class frequency of ith class, and TB is just a scaling factor which we can tune as per all.
That's a temperature scaling.
Yeah, temperatures. Okay, go back. So yeah, each. So when we minimize this loss function, we can
This
see.
is a kind of propensity weighing, is it? So there's a notion of propensity, which is it's the tendency of rare classes is that they tend to get rarer. That's a propensity.
Right.
For example, if there is a Wikipedia page on, say, Abdul Kalam, um, most often, uh, even human annotators would identify, Abdul Kalam to be former president of India, maybe a big ISRO scientist, but
Right.
maybe he studied at some college. As a graduate of alma mater, had his alma mater was, say, some engineering college. But the propensity of not tagging Abdul Kalam with something which is less popular. I mean, the college may not be as popular,
Uh,
but that doesn't mean he didn't study at that college.
right.
So I'm just wondering, people in the extreme text classification literature looked at this propensity loss. This is just the same, looks like the same, right?
Yeah. It is just like the normal softmax loss which we are minimizing. So like in the second step, we can see it will restrict the most common classes. It will penalize them, and we'll see more of the less common classes according to this. So class aware margin, this is similar to the previous one, but in this we are giving larger margin for the frequent classes. So trades regularization, in this we incorporate a scale divergence term, which encourages the similarity between the adversarial input as well as the normal input. So we'll do ablation on all of these, and we'll see which gives us better robustness and efficiency and all that. Go next. So here in the result, we can see that Robal gives us the best in almost the best in everything, but it takes double the time as well as almost double the memory. But as we can see, ATBSL is very great as we compare it to it. So uh, so that will incorporate further with data augmentation and see how well it has performed. So So even though we were using ATBSL, what we found out was that there was a robust overfitting on CFAR 10 LT as well. That was because that what we were using was a constant learning rate. So and if we use a learning rate that decays as we go further in time, as the time steps elapse, we'll get a proper loss which is robust as well as efficient, but that cannot generalize to all the images in the world. So what we'll do now is that we'll address it by using data augmentation. So these are all the data augmentations that are used. The blue line just denotes the normal ATBSL, and the green and the orange line denotes shows ATBSL along with mix-up and cutouts, etc. Go next. Next. Yeah, next. So this is just how rand augment is used. So out of the 14 transformations like shear X, shear Y, Fourier transform, etc., we take two of those transformations and we add it to ATBSL, and then we obtain the final thing. Go next. Go next. So these are three of the transformations which, when used alone, perform really poorly on the data set. But when we combine all this, we'll get a well-defined, a very well and robust.
What does solarize mean? Solarize is a transformation. Auto contrast is a transformation.
It is just a transformation, like an image transformation, just
What
like
does it do?
so. Solarize, like, I think it brightens up the image a bit.
Okay.
Yeah. And auto contrast is just a normal contrast which we use like
You are saying that when used alone. So you need combinations.
Yeah. So when the three of them are used together, we'll get a better a better algorithm for it. So go next. Go next. Yeah. So when these are used alone, we'll get a suboptimal result. But when they are used together, we'll get the as we incorporate more number of augmentations, we'll get a better one. Next. So yeah, here we can see when these are used alone, we are getting not so great results, but when they are used together, we'll get next. So this is just a training setup. So these are all the attacks that we are performing, that the adversary performs, and these are the comparison methods. The second slide which I showed you, the AT-BSL along with data augmentations gives the best results, and this is all the training description and everything. Yeah, next. Yeah, over.
Hello, I'm Srijan Jha. I will be presenting a simple contextual learning paper. So the main idea of this paper is to use self-supervised learning to classify images. Uh, it basically uses a high quality visual representation without any labels. So the key components of this this framework was to use data augmentation. They do like very simple augmentation like cropping, Gaussian blur, color distortion, and they use standard resonate as the encoder, and and they use MLP with one hidden layer to get the to apply contrastive loss and for two similar images, they want to put them to as close as each other in the embedding space and to push apart the different images. So they use contrastive loss, which maximize similarity between two positive samples and try to minimize similarity between negative samples. And the key insight of this paper was that data augmentation is really essential. They use some like specific augmentation technique, which give very good results. They use non-linear projection head, which help them in getting the loss. Uh, they uh, they have like usually larger batch sizes because then we will get more number of negative samples. And, yeah. Yeah. The motivation was Yeah, the motivation was to use this loss function so that without any label, without like so this is self-supervised learning. So without any label, they can use just based on the features. They can sample, they can extract features which help them to like cluster cluster image like two same images which are kind of same but they have been augmented to came close in the embedding space and push apart the different images. Yeah, clustering. Right.
So the entire contrastive learning is being done within a batch. So you are contrasting within these augmented views of each image are all in the same batch, right?
Uh, Yeah, so in a batch, there is one image anchor, then and there is a one positive sample, and all are negative samples. So the idea of this loss function is to the feature representation to maximize the similarity between the positive and the anchor, and just to sum apart others in the embedding space. So these are the results of the paper. Like top one accuracy on ImageNet, they got like 76.5% with ResNet architecture, and with top five they got 85.8%, and like, which was like fine tuned on only 1% of the label. So, like the clustering is the clustering part was like the oversimplification. Like it was training so that the feature space should it should extract feature, and in the embedding space, two positive the features of the features should be as close as each other in the embedding space of the two similar image, and like as apart for the negative samples. Yeah. So coming to our project proposal, so we are gonna generate the synthetic images as mentioned in the first paper using those LLMs and text to image models. Then alignment will be done with the contrastive learning part, and then for the robustness we'll start with PGT based attack, uh, and we'll use both real and synthetic images for the training. So these are the loss function, final loss.
You again muted, is it? You muted yourself. Basically, additive will defeat the purpose, right? I mean, just doing a law summation likelihood. Maybe you want to think a little bit more about this feedback. Okay. Anything else? Anyone else?